Good morning, everyone. It's nice to see all of you here today for my dissertation defense. So the title of my dissertation defense is Computational Analogies in the Era of Large Language Models.
Oh, this is a full stop. Pause. This is not working. Pause the recording. Wait, why is this not working? This one. Huh?
There's one working, Dr.
No,
J.
but she needs to be picking back
No,
up.
this is speaking.
Okay. Will this work? No, this one is fine. No, but let's put it here. Because the quality of voice is much better than. Yeah, put it. That's fine. So this will catch. You put it here.
Okay.
All right. Can you make the mic this one?
I think this is fine. That's fine. This is fine.
Okay. We want voice to be.
It should be fine, Dr. J. Should be fine. We checked before.
You can't redo it. See, that's
Yes.
Yeah, I can hear just fine, Thilini, just fine.
Okay. Thank you, Dr. Shalin. So this is my dissertation defense titled Computational Analogies in the Era of Large Language Models. And my dissertation committee includes Dr. Amit Sheth, who is my advisor, and Dr. Marco Valtorta, my committee chair, and Dr. Michael Hunes, Dr. Amitava Das, Dr. Valerie Shalin, and Dr. Srinivasan Parthasarthi. So let's move on. What are analogies? So let's begin by understanding what analogies are. So we use, in a very high level, we use analogies to identify situations, novel situations, in terms of situations that we have known before. So we try to map things that we know from a certain domain to another domain that we don't know. That is basically analogy. And the classic example for an analogy is the one that in a lot of classrooms that we use is when you're not very familiar with the concept of atom, right? So the teachers would use the concept of solar system to explain what an atom is. So you try to make these relational mappings between these two domains, and that is called an analogy. So in general, there are 4 parts for an analogy. One is the source, which is the familiar situation. And then there's the target, which is the novel situation. And there are mappings from the known domain to the target domain. And then we have inferences. So this new knowledge that is gained of the target. So these are in general the 4 parts of analogy. And moving on. So there are several theories of analogy in different areas of research. So in cognitive science specifically, there are several theories. So I've picked 3 here. So these are like prominent ones where one is called structure mapping theory, which is introduced by Gentner, and they focuses on structural similarity and the relationships among these different domains. So it's relational focused. And then later in the multi-constraint theory by Holyoake and Thagard, they extended this by incorporating semantics. So semantic similarity and then structural consistency and also pragmatic centrality. So then later, Hofstadter's work was focusing on the conceptual fluidity that emphasized that analogies involve flexible, content-dependent representations. So those are the theories in cognitive science. And if you move on to linguistics, right? So this is very popular book, Metaphors We Live By. So Lakoff and Johnson, they showed that metaphors shape our thinking through domain mapping. And all of these theories I talked about earlier in cognitive science were converted into computational programs. So one is structure mapping engine for structure mapping theory that I talked about. Then for multi-constraint theory, there is this analogical constraint mapping engine, and later Hofstadter's group, they introduced the copycat, which looked at fluidity in analogy. So what I want to emphasize here is this proliferation of analogy theories across different disciplines reveals a fundamental truth, that analogical reasoning is both central to human intelligence and it's remarkably complex. So no single theory captures it all. So this leads to my thesis statement. So analogy making is central to human cognition. It requires the effective integration of abstract reasoning, pattern recognition, and background knowledge. Despite significant advancement in language modeling techniques, the ability of current methods to accurately identify, model, and evaluate analogies remain fundamentally underexplored. So in this thesis, I try to contribute uh, towards bridging this gap. So let's move on. So I just want to highlight here, so why do we need to explore something like this? What is the end goal? What is the end motivation? So one hierarching motivation is that human creativity is deeply rooted in analogical reasoning. So this is our ability to draw connections between seemingly unrelated concepts, right? And then transfer insights across domains. So if we can develop machines that can do this uh, as we do it, that has that capability, they can not just assist us, but they could be truly collaborating with us. And this could accelerate discovery and innovation in ways neither could achieve alone. So this is a good motivation that we think that would drive our research. That is driving our research actually. So I just want to highlight, in a very recent interview with Demis Hassabis, a Nobel laureate and the CEO of DeepMind, he was emphasizing the importance of analogy and how it is important in creativity. And if we have machines that could do what humans do in analogy and creativity, these models could be nearing AGI, so artificial general intelligence. So moving on. So now let's focus on the contributions. So these first three contributions I have explained in detail in my proposal defense. So I will not go into the same detail, but I will explain them briefly. And then the fourth and fifth work are the ones I'm newly introducing and explaining. So let's look at the first work. So towards efficient scoring of student-generated long-form analogies in STEM. So in this work, what is the question we are asking? What are the discriminating features of evaluating strong and weak analogies? So if you can see to your right, that we identified features under four types. So semantic features, syntactic features, statistical features, and sentiment-based features. And also we created for each analogy sentence in our data set, right? We created feature vectors based on Elmo embeddings and ConceptNet number badge embeddings. So now we have embeddings and we have hand engineered features. So what we do is we use them individually for evaluation task of good analogies and weak analogies, and we combine these features together, and also we do the same evaluation. So what we figured out is between hand engineered features versus feature vectors, right? So Elmo, which is a language model based feature vector, it has the highest performance. But if you combine it with hand engineered feature, you get a slightly higher score. So it suggests that there is something in this hand engineered features that uh, supports a discrimination when it's connected with Elmo. And then we look at how the distribution of semantic and syntactic features uh, in the top 15 discriminative features. And we see a lot of features that are discriminating falls under syntactic and semantic features. So these are the kind of key takeaways for this work. And then I'm moving on to my second work, which is the Analogical, a benchmark based on a taxonomy to evaluate analogies. Um, so let me situate my work in the previous literature. So in computational analogy making literature, starting from 2008 onwards, there were researchers working on analogy and identifying analogies, introducing data sets and introducing methods to evaluate analogies. So looking at all this research before us, what we saw was there was a focus on single word or multi-word analogies. And also in LLMs, uh, in most cases, they are based on extrinsic measures evaluations like glue or superglue. So in our case, we kind of extend both of these directions. So we try to quantify analogy complexity, not just word level, but we try to see what are the other levels there that we can use. And also, we do comprehensive evaluations on LLMs. So previously, other researchers actually did this evaluation, but on a limited set of LLMs. So we extend that work to more LLMs also. So let me present this analogical taxonomy. This is a structured framework that organizes analogies by increasing complexity. So as we move up this pyramid, analogies become progressively more challenging along three key dimensions. One involving more words. So you have more words at upper levels than level 1 or 2. And upper levels require greater compositionality because you have sentences and paragraphs. And then they depend on increasingly abstract relations as you go up. So I'll talk about this later on my work also. So, so very briefly, at the base, we have simple words, and moving forward, we encounter word sentence mappings, and then syntactic analogies and negations are also there. That can be considered as negative analogies. And then we have entailments that involve semantic relationships. And finally, we have the metaphors at the top. Yeah, this is the most complex form in this taxonomy. That require mapping abstract relations across different narratives. So what this hierarchy supports is it allows us to systematically do the evaluation and see where LLMs excel and where they struggle. So these are quick statistics on our data set at each level. So in certain cases, we borrow directly from previous work, previous data sets, and in some cases, we derive data sets from early data sets. So derived ones are marked with stars. So moving on, I just want to highlight the LLMs that we evaluate with this work at that point. So we try to get a balance between different architectures. And moving on. So this is where I would like to focus. So this is kind of the results. So I'll explain what is happening here. So we hypothesize that the distance between two elements of an analogy should fall close together, or that distance should be small in the embedding space of an LLM. So what we see is that in the at this word level, so here, and at this level, it seems like they're struggling a bit because the uh, um, distance should be smaller, but it is high, even for the best performing models. I'm listing the best performing models here. So so this actually motivated the rest of my work. So I wanted to see what is happening at each end. So I do one work that focusing on these word level datasets and one work on the other end of the spectrum. So moving on, I just want to highlight a few things here. So key takeaways, straightforward. We introduce a benchmark based on different complexity levels of analogy, and we evaluated 8 LLMs using this benchmark. And we demonstrate that identifying analogies at both ends of this taxonomy presents a challenge for these models. I want to highlight scope and limitations of this work. So this benchmark focuses on pairwise similarity in embedding space. So we are not actually looking at any explicit mapping or any discovery of analogy or any reasoning chains. We are not looking at any of that. We are looking at just pairwise embeddings in an embedding space. And so as you saw, most of the data sets in that data set provides only positive analogies. There's one data set for negatives. But I want to say that without negatives in certain cases, this could result in statistical comparisons maybe being distorted. So specifically if you're using correlation analysis and all that. So moving on from this work. Now, I briefly looked at inner workings of LLMs and how LLMs identify analogies, looking at how they create embeddings and all that, like probing mechanisms. So this work does that. Okay. So this is the question that we ask. So is there a connection between LLM's ability to identify analogies and their ability to encode sentence structures? So if they can encode sentence structures in certain ways, are they better at identifying analogies? Is there a connection? So because initially we wanted to figure out what these results meant in our case. That is why we went through this route. So to do this, we need 3 scores, right? One is the analogy identification ability. We need a score for that. And then we need we need to quantify the semantic structure encoding ability and the syntactic structure encoding ability. So these 3 things, we try to look at the correlations. So I'll very briefly explain how one would calculate the SEM score and the SINT score. So let's say you have this sentence, and there are traditional methods that you use to parse a sentence in its syntactic structure. So you have that structure, right? And then you send the sentence through a language model. Then you have the sentence embedding, and there are probing techniques introduced that you can probe a structure out of that embedding. So you can get a graph structure out of that embedding. Then you have this, let's say, the goal graph that you created through traditional methods, and the other graph that you probed through the LLM embedding, and you try to see whether these things are mapping. So if LLM's graph is really good, like that it maps with the traditional one, okay, maybe LLMs can identify sentence structure better. So that is what is the very high level detail of this work. So what we did was, there were already mechanisms to probe and create these scores for syntactic parsing, but it was not there for semantic parsing. So we extended it for semantics parsing and then do the comparison or correlations. So this is the key takeaway. So
Thilini, Thilini,
yes.
could you offer a little more explanation of what it took to go beyond syntactic to semantic, like what you actually had to do to get to these results?
So we had to do two things. So we had to figure out a semantic parsing technique that is there are techniques out there. We had to figure out a semantic parsing technique that aligns with the probing technique, actually. So it is a bit of tinkering and engineering on that pipeline. So once you have that semantic parsing, then you could extend that to probing and then these scores. But what we did additionally added was, one other thing is that they were designing this course for certain LLMs, but not certain other architectures. So we extended to that architectures too. So those are the ones that we specifically did.
Thank
Did
you.
I answer you, Dr. Patsat?
Yes, yes. Thank you.
I wanted to ask a question just to understand. The formulas for under 2 and 3, since coincidence are formally identical. So where is the difference?
So these when you do the probing, so the scores are the same score, but the the data points that you use to generate these scores, they are different. So in syntactic structures, it is based on syntax. In semantic structures, it is based on semantics. So its starting point is the different thing.
That's good. Thank you.
Thank you. So moving on. Okay. So what is the key takeaway? So we looked at Spearman rank correlation and Kendall's rank correlation to see what are the correlations. So what we saw was analogy analogy score and syn score, they correlate significantly, but analogy score and sem score did not have a significant positive correlation. So in a very high level, when the LLM architecture can capture syntactic structures better, it shows higher capacity for analogy identification. So that is what we figured out. So, okay, so moving on. Okay, so this is the fourth work, and let me talk about the motivation for this work. So this is called knowledge prompts, solving proportional analogies via knowledge enhanced prompting. So first, the motivation. So I told you before, right? We saw these results and we wanted to figure out what is happening here. So that is what we are doing basically. So the question we asked is, can we improve the performance of LLMs on proportional analogies? So what is here is it's in the domain called proportional analogies. And when we can we improve the performance on those when we provide external knowledge? So let's look at what is a proportional analogy. So you probably would have seen this type of questions. These are mainly coming from SAT questions that used to evaluate linguistic and the abilities of students. So what happens is there are two words that share a certain implicit relationship, and there are another two words that should have the same implicit relationship. And if that's the case, you call those proportional analogies. So oxygen and gas, what is the relationship? It's type of. And what is the other two words that have the same relationship among these answer choices? That is basically the question we ask from the LLMs, and in normal SAT questions that is asked from the humans. So yes, let me try to go here. So so what we did was, there were several data sets from previous work that were looking at these SAT type questions, basically MCQs, but it was limited, and a lot of them were under maybe 400. So what we did was, we combined all those to, then they created 1000 MCQ data points. So this is from previous work, and we wanted to extend this data set to have more data points and data points with more different implicit relationships. So that implicit relationship we had type of. So how many more there can be? So most data sets have this very limited semantic relationship amount, like the types. So what we did was we generated 14K MCQA data points based on this seminal work by Yuan et al. So they actually created an analogy knowledge base. I will not go into details, but they based their analogy KB on ConceptNet and Wiki data, and they kind of directly utilize the concept pairs in that knowledge graph to create their analogy KB. So what we did was simply, actually, this is how we created very straightforward the MCQA dataset. So we have a 3-way or 4-way answer choices for a question, right? So we try to create a pair of terms representing the question, and then there are again n pairs representing the answer choices, right? Only one should be correct. So the semantic relationship between the term pair in the question should match the term pair in the answer. So that is what we did. We randomly kind of created this answer choices. So that is how we created the data set. So we combined the 1,000 data points and the 14,000 data points to create 15K. And we evaluated on that. So this is dataset statistics. So I just want to highlight this dataset is 15 times, this has 15 times more data points than previous smaller datasets, and it has 10 times more implicit relations among term pairs. So now we do a evaluation on this dataset, and how we do that is this. So we use different types of knowledge in the prompt that we send to the LLM, and we basically ask the LLM to give the answer similar to a human, right? So I'll just show you the zero-shot prompt example for this work. So we have the question, we have the answer, we have a very short instruction for the LLM, and we prompt it for the answer. This is the one-shot prompt example. So for few-shot prompting, we have 1 shot and 5 shot. So what does it mean by 1 shot? We just give one example for the model to look at, and then it would look at that. It would look at the answer, probably learn from that, and then we give the real question. And for 5 shot, you have 5 examples. So when we pick the 5 examples from our dataset, we try to pick the 5 that are most semantically similar based on embeddings, semantically similar to the question. Yes. So this is the interesting part, how we incorporate structured knowledge in that prompt. So initially there were no knowledge, or there were just examples. So how we would incorporate structured knowledge in this case. So when I say structured knowledge, we looked at 3 sources: Wikidata for world knowledge, ConceptNet for common sense knowledge, and WordNet for lexical relationships. So there are very straightforward 3 steps. So first, you do the knowledge retrieval from the graphs that you have. So we based upon Lin et al.'s work. So what they did was, they did not really look at subgraphs, but they look at paths. So in our case also, we are interested in paths because we are looking at analogies, and it is very focused on path relationships. So we kind of extracted these knowledge paths of length k, and we have cutoffs for k for Wikidata and ConceptNet. And so however, we have these paths retrieved, and there could be several paths retrieved for certain word pair in our data set. So how would you filter? Because we can't add everything in the context window right now. So we were thinking of a method to filter it. So we very straightforward look at semantic filtering and random filtering. So you pick something at random, or you look at the most semantically similar path to the term pair. Again, that is embedding based. We encode it with a sentence word encoder, and then kind of see what is most semantically close. So once you have your picked up path, that is the knowledge path, the knowledge basically, you kind of attach that to your prompt, right? It is something like this. For all answer choices, you have the knowledge that you've gotten from each of these knowledge sources. So this can be very long, and we can say it's noisy. So moving on to the next prompting technique. So here, probably a lot of you have heard of chain of thought prompting. So in chain of thought prompting, what you do is you kind of nudge the model to initially you show the model, okay, this is how you would reason, and then do this like that, the similar reasoning. So in our case, we wanted to do kind of chain of thought, but it is not conventional chain of thought. So we provide, we don't provide any examples, but we provide knowledge in the sense that in two ways. So we directly give it, okay, this is the implicit relationship between these two question word pairs. So now the model knows that. And then we say, okay, as humans, we would, when we pick the answer, we would look at a term pair that has the same implicit relationship. So that is the process for a human to do that. We give that process to the model to see what happens, right? So, yes, these are the results. I'm only, yes, picking, I'll explain these two very quickly because they were interesting. So the overall performance was the best on the most recent model at that time, GPT 3.5 Turbo.
Thilini, can you explain the metric here? The EMA metric?
Oh, yeah, I'm sorry. So it's actually exact match accuracy. So,
Mhm.
so if you basically, if the LLM say whether it's, so we ask the LLM, tell the number of the correct answer choice, right? So it
Okay.
has to say exactly 1, 2, 3, or 5, no partial matchings or nothing.
Okay, so in that case, there is a chance baseline, correct? That is dependent upon the number of options that you offer. So you have a probability of getting this correct by chance of 0.2 when you have 5 options, 0.25 when you have 4, etc., right?
Yes.
Okay, so I want to know in this chart how you handled the fact that you varied the number of options in your testing scenario.
So in this case, we do not specifically look at chance, how that happens, how based on chance, like by chance, how it would get an answer.
Okay, so but did you mix like 3 options, 4 options, and 5 options in your test?
We mixed,
Okay.
in sense, mostly overwhelmingly it is 5.
Okay, so then in that case, when we look at these numbers, and you just got rid of the chart, but when we look at the EMA numbers, we can tell how good a job it's doing relative to chance. So in a 5 option situation, chance is 0.2, and so Falcon is in zero shot prompting doing just a hair better than chance, right? Is that the right way to think about this?
Um, yes, 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 true.
Okay.
They don't perform actually really well. That is a problem here. So even with targeted prompting. So yes. So we see at least
And then,
targeted.
just one quick thing. You have some below chance performance as well.
Yes, I
Below
think.
chance, usually when we evaluate human performance, that usually means something, below chance.
Okay.
Systematic error.
Okay. One thing I would like to highlight here is that one would expect that adding structured knowledge would improve the performance, right? So what we see is that it actually decreased. For GPT 3.5, zero shot, without no knowledge at all, it performs better than when you give it structured knowledge. So this was interesting to see. So one thing could be this is a cognitively demanding task, and just adding knowledge would not do anything. So you need to think about how to add knowledge, what to combine. So it could maybe be noise. So this is a good area to pursue further for this line of work, I believe. And then we looked at, so we talked about the implicit relationships in the data set, right? So we looked at in targeted knowledge prompting that performed the highest. What happens with each of the relations? So we see that certain relations, so I need to move fast, but we see that certain all the relations, they don't perform really well, but certain relations seem easier than the others. So that is the analysis that we did for this work, semantic relations. So it's part of and follows. These relations emerges to be very difficult, and at location seems to be easy for the models. So yes, moving on. So the key takeaways. Even with external knowledge incorporation, even with targeted knowledge, proportional analogy identification remains challenging for the LLMs. And yes, so there are scope and limitations for this work. So we use manual prompts, and there are research saying that if you change a manual prompt even a little bit, you would get drastically different results. So there needs to be systematic exploring of this multiple prompting techniques to get a robust prompt. And also, so we provided targeted knowledge, right? But that targeted knowledge does not come cheaply. So we had to annotate 1,000 data points in our data set to with humans to get that targeted knowledge, that semantic relationship. So if there is methods to kind of do that automatically, it would help in these type of situations for LLMs at least, but not much as we saw. But then graph completion, because we saw that only 20% of the data points in our data set had knowledge from all the three sources. So this is a problem with graph completion. So, but that is a limitation that we have for our work, getting the knowledge. And finally, we are here at analograph. So this is where we try to evaluate realistic long text analogy generation and evaluation. So this is this has two parts. So one is this data generation, and the second part would be this data evaluation. So the motivation, right? These are the data sets that this is an example of a data point from a data set that has long form analogies. So you see that they are very, like, they map very easily, right? They're very clean. But think of, in your mind, things, analogies is not like this. It's connected to everything. So we felt like we looked at several data sets that are like this. And this is the motivation. So data sets with data points that have pre-aligned structures with immediately apparent correspondences allows the model to bypass the core challenge of analogical cognition, extracting representations from complex situations. So you do that for the model and then ask the model to map. Is not actually what is happening in the real world or in humans. So we kind of wanted to create a data set that reflects the real world more. So I'll move quickly. So this is the overview of the data set. So we introduce a pipeline to generate more realistic long analogies, right? So what we do is, let's go back, right? So let's say you have a data set, and that data set is, you have a data set that you think is very clean. So what can you do with that? Can you add noise realistic noise to that. So that is what we are doing. We have two pipelines, stat noise and xno pipelines. When you have a data set, you add knowledge with these pipelines. Let's say you don't have any data set and you would like to create a data set. Then if you have a domain knowledge graph or some knowledge graph, you can mine this type of realistic analogies from that knowledge graph. So that is the CN mined pipeline. So I'll quickly talk about each of these. So the core idea here is for stat noise, you kind of capture the global statistics of the data set and later use it to pick the noise. So you use that to pick the predicates and the objects. And once you have these triples, right, based on this equation, so you kind of try for predicates. I'll explain. For predicates, you try to balance between the global distribution of predicate and the predicate distribution conditioned on the subject. So kind of try to balance that. So any user can have this lambda and balance that in a way that they like, and then they create this predicate. So similar for that for the object selection also. So once you have these triples, you kind of filter them for to remove the self loops and to remove the self loops and to maintain uniqueness. So you don't want to add several same triple to your data set. And then once you have these triples that you would like to add, you will inject them to your trip graph basically. So you could add for non-analogies, you pick, so you have two graphs, either could be analogy or not analogy. So you add noise to one graph, which is asymmetric, and you add noise to the both graphs, and that is symmetric. That is for analogies. So then we look at the XNO pipeline where we sample a noise from external data sources. So we basically construct a lookup table mapping entities to their semantic neighbors, and then we kind of sample from that. So that is the external knowledge usage here. So in this case, we use WordNet and ConceptNet. So we get from both of these sources and try to combine, and then again filter with the same criteria, and then inject that to the original graph with the same criteria. And moving on. So this is in this pipeline. So this is when you don't have any data set. You just have the graph. So you just get the graph and you try to do structural path mining based on bounded depth first search, and you find simple paths, right, of length L that the user who is using this pipeline can define L, and then you pick paths with the same relational signature as in here, and they would be the positive examples, and for negative examples you would corrupt one of the graphs. So you could do select an edge, replace its object with a subject of another edge, or you could select edge and reverse the direction. So this could corrupt one graph and not have that analogy that you had. So this is how.
Do you have an example of this?
Not right now in this, but I have in my thesis. I will have in my thesis of what. So
Thilini, could you repeat the question, because I don't think it was very clear to people on Zoom.
Okay. So Dr. Parthasarathy, Dr. Humes asked whether I have an example for this negative sample generation. So right now I don't have an example right now here, but I have one in my thesis for this. So now you have the analogies or non-analogies. Now you want some noise also. So for n nodes, n nodes, you could add k-hop neighbors to certain n nodes, and that would be your noise. So now you would have certain analogies with noise, right? Okay, so I explained all the pipelines. So once we have these analogies, we merge and we deduplicate, and you can kind of create a final data set. So here we name it as analogy. So this is for this particular case, this data set looks like this. So we have we have 3,870 analogies, and from the source we initially had very clean close to 1,500 analogies, and then we mined from the knowledge graph that we had ConceptNet 1,000 analogies and 1,000 non-analogies. So this is the statistics. So you can see it's fairly a balanced data set. And then we move on to evaluation of this data set. So at a very high level, long text analogies, right? They span multiple sentences with compositionality, coreference, and ambiguity. So even with triples, you have several triples now. Now it is tougher than the word level case. So in prior data sets that were very clean, it would have been easier. But in this case, we evaluate what is happening, right? So we have two complementary evaluations. One is we use LLMs. So these are like sequential text encoders. So we use a zero-shot prompt with LLMs, and then we use graph neural networks as graph structure encoders. So I'll just go to the results of the LLM. So what we see is that all models are better than random baseline, but they remain moderate. The best accuracy is around 70%, and best F1 is also around 70%. And this could point to a fundamental limitation of this transformer style architecture, not just this certain specific modules. And you can see the prompt that I used there. And then we move on to
Just a
the
quick
graph.
question. Just a quick question, Thilini. Olmo recall is 100. I mean, that is surprisingly 100. I mean, if you go back to the previous slide.
Yeah, but yes, it was surprising, but precision was very low in that sense.
Okay, I'll ask more question later.
Okay.
I guess it finds all the analogies, but it also finds some bad ones.
Yeah, a lot of bad ones. So, Dr. Das, I'm moving.
Found something.
Yes, please.
Yeah. Okay.
Verify it later.
Okay. So this is the GNN architecture that we used. So we use CMS architecture because we are looking at two things together. So we have shared weights, and we specifically use this graph neural network architecture called graph isomorphism network. And it is edge attributed. So it takes into account the edge attributes. We do that because in analogies, edges are very important. So that is why we wanted to kind of use that knowledge in the pipeline. So what you do is you train this model, the analogy, whether this is a binary classification, so whether some two graphs are analogous or not is in this case based on distance. So it's based on thresholding. And so now we have the results for GNNs also, and we compare with the LLMs. So GNNs have the best F1 and accuracy and a strong recall. So here, actually, this is what Dr. Das also asked. There are models that have very high precision and also but low recall and very high recall and low precision also. So, but you see that GNNs have the balance of the both. So now with that, yeah, that section is coming to an end. So all my contributions I have discussed now. So I'm moving to the dissertation contribution summary. So very quickly, I did work on scoring of student-generated long-form analogies, and we introduced a discriminative analogy feature pipeline, and we identified syntactic and semantic features as top discriminators. And then we move on to analogical, a novel benchmark for analogy evaluation, and we introduced a taxonomy-based benchmark spanning multiple complexity levels, and we demonstrated that LLMs struggle at both the word level and the long text level. And then we looked at sentence analogies and how sentence structure identification in LLMs help identifying these sentence analogies. So we extended this syntactic structure probing methods of LLMs to semantic structure probing, and we showed that better syntactic structure encoding correlates with strong analogy identification. And then we looked at how we could enhance prompts with knowledge for proportional analogies. And we demonstrate that even with external knowledge, these tasks seem challenging for LLMs. And then we move on to analograph. So, and here we introduce a pipeline to generate more realistic analogies. And also we showed that edge attributed graph structures outperform LLMs in these realistic long form analogies. So,
Thilini, just abstract here, and you can address this later on if you want to. But you see, currently there is a lot of interest in using knowledge or structured representation to improve some functionality of LLM. And what you have done is to look at that in the context of analogy, long analogies. And I don't know whether you can call it just long analogy or long and complex analogies. But to, you know, I like to get a good feeling of to what extent you can convincingly show how much LLMs can be improved with this knowledge or any other way, or this analogy, and if not, why? Because that is a fundamental question. A lot of people are going to, just today while driving, I was watching a YouTube video, and that's all about using symbolic information with networks. So it's a fundamental issue. Analogy represents a complex problem. To what extent you can conclusively show, yes, LLMs can scale or be improved with these methods, or no, we don't know yet whether it can at all be improved.
Okay. So I should answer now, or?
Your choice.
Okay. So I'll choose to answer now. So from what I have seen from my work, what I've seen is that it's not about you adding the knowledge. So there needs to be several aspects that you need to really look at. So because we were the ones to first do it for analogies, we kind of created these benchmarks that other people can build on. But what I figured out is, what does it mean to add analogy? Is it just you add in the prompt in a certain way? And what is knowledge at that point? So is it the path? Is that it? Or is it, as we call, the targeted knowledge, the specific reasoning chain? So there needs to be a lot of research on that area of what do you call knowledge and how you would combine it in the prompt if you are going that route, or in other ways, embeddings, how you would combine that. So the most important question I think is to ask is that, what is the point when you add knowledge that it is not noise? Because right now what I'm seeing is, at least what I'm speculating is, when we add knowledge, it could be noise to the LLM. That is what I'm thinking from what I've seen. No, even without encoding, even just as it is, right, in prompts. Yeah. So
But
how would,
when you're prompt, it's still converted into method.
yeah, that's true. That's true. That is true. So at at which level then would you want to figure this out? Or how would you add this? At which point and which knowledge? How would you combine when you have several knowledge sources? All of these things are very rich areas to actually go towards, and like,
Do you think you can write an article on why exploiting knowledge in LLM is challenging or complex problem solving?
that would be a very interesting article, but you need to do we need to look at several problems, not just analogy. You'd have to look at several problems and several knowledge graph, knowledge encoding techniques, like combining techniques and all that. But I think that is very interesting to do, because we are just saying, okay, we can add knowledge, but there's a lot of questions that you need to answer when you just say that. So that is what I think. Okay, I just want to connect everything here in my broad impact. So there's this hanging arrow, but bear with me. So in the very beginning of my thesis statement, right, I talked about that the ability of these current methods to accurately identify, model, and evaluate analogies remain fundamentally underexplored. So in my thesis, I try to bridge that gap and explore different areas of analogy making to actually bridge the gap. So first, my work in ICCBR 2022, a workshop paper, we explored the discriminating features of student-generated analogies, right? Next, we built a benchmark to explore how analogy is represented in LLM embedding space. So asking, can embeddings capture relational similarity? Then we explored how semantic and syntactic mapping abilities of LLMs affect analogy identification. And then we explored, what about external knowledge? How can we, like, does it help? Does it not help? And then I looked at, in the work that is in preparation, I looked at what are the other methods beyond LLMs that we can use for analogies. Maybe you can combine those. So I want to highlight that my dissertation does not just provide or propose one model. So we try to build a conceptual and empirical staircase that collectively address why analogy making remains hard for AI and how we can start making it tractable, and through my contributions. So there's a lot to explore in this area. So we are trying to create this baseline, and we hope that a lot of other researchers, right now, a lot of people are coming into this research space, building data sets, building models. So it's nice to see. So this is my PhD journey. I was very fortunate to not only get to do the publications, but I got to do a lot of other things in my PhD journey. So I got to mentor several students and talk to them and understand how they understand things, and they would ask questions, and it drove to interesting things in papers. So and then I had collaborations with several interesting people at my research internship at NLM, and also with other external collaborators.
Thank Olivier.
Yes.
For joining here.
Yes, I talked to Dr. I emailed him yesterday. So we have some publicly available resources. Also, I'm grateful that I got to do academic service as an area chair, a program committee member, and a reviewer. By reviewing a lot of papers, I understood how not to write papers, basically. But it was a very good experience. And with Dr. Shet, I've worked in several grants. We wrote 3 NSF grants, and we also wrote 1 industry research proposal. And yeah, so this is my PhD journey, and I'm grateful that I had all these experiences when in my time here. So this is now to thank everyone. So first, I like to thank Dr. Shet. So your guidance was not just for my PhD, but I think it's for life. And I thank you, and I'm very grateful that you trusted me and gave me time when I most needed it, so that I could focus on my work. And Dr. Shalin, I was always very inspired by how you knew literature on your area. It was like a story, almost like a story all the time. And I always wanted to do that for my area. And so you inspired me on that. And Dr. Das was a very pivotal point in my PhD journey. He showed me that bold action always trumps uh, endless deliberation. You just have to go there and do that, Thilini. He would just tell me that. So I learned that from him. And I like to thank Dr. Humes and Dr. Parthasati. You actually gave me very impactful and insightful comments that I used actually in my work and my research. So thank you for that. And Dr. Valtota, it was always fun meeting you at these graduate meetings. And I thank you so much for your comments and also making sure that this dissertation runs smoothly. So you do that for all our students. So I thank you for that. And so by collaborating with all my co-authors and collaborators, I learned a lot. I learned from each one of them. So it was a great opportunity. So I'm very grateful for that. And I'm also grateful for the funding agencies that made this path possible. And so let me thank my colleagues here at AIISC first. So we had a lot of discussions, and maybe they did not materialize to papers, but they did materialize to cherished memories that I will take with me. And you guys were a great support system. And I also want to acknowledge the Sri Lankan community here in South Carolina. I don't have enough words to express the gratitude. And then I wanted to thank my parents and my in-laws. So my parents actually taught me perseverance trumps everything. And also I want to thank my brother. So I'm here, and my brother is the one who is taking care of my parents, so I can do this work really well. And my in-laws for understanding me. And finally, but not last but not least, I want to thank my husband, Ruwan. So he's my toughest critic, and he's my best cheerleader. So that balance always pushes me forward. And I like to thank my daughter, who actually made me realize what actual happiness is and also what responsibility is. So I thank her for that. And yeah, these are the resources and references for my work. And yeah, that's it. If you have any questions, feel free to ask.
You might have to repeat my question so that people can hear it. So you began with the classic analogy between planets and atoms. What kind of analogy is that? Is it sentence? Is it proportional?
So you can make it into different things. So you can say sun is to atom, as in, and use it that way in a proportional analogy. But let's say you have two paragraphs, one explaining the solar system, one explaining the atom. You could say those are long text analogies because you have paragraphs now, sentences. Or you can say it in one sentence about the solar system and one sentence about the atom, and then it would be a sentence analogy.
Okay, so considering it as a sentence level analogy, that planets revolve around the sun. And you could parse that syntactically and semantically. The important word or the important structure is the verb revolve around. So when you analyze analogies syntactically and semantically, do you take into account which segment is the most important?
You have to, and based on a lot of cognitive theory literature, it's always the relationship in because
And so when you did proportional analogies, you emphasize the relationship.
yes.
Did you emphasize the relationship when you did your syntactic and semantic analysis?
Yes, in the sense that in semantic graphs and syntactic graphs that we have, so it says how this is that a verb, or in the semantic case when you pass, is that adjective, or like that you have that relation structure there also. So in the probing case that we had for the large language models, we take that into account, but it is through the embeddings actually.
Okay, so how does that affect the story?
So
Is it like relationships are 10 times more important than the entities, or 2 times more important?
so I don't think with the embedding case, I can tell, I can actually quantify, but from the graph neural network work that I am currently doing and that I presented the preliminary results, I think the graph neural network that we design specifically take into account the edge attributes. So basically the edge embedding. So it actually gave 75%. So that's a good start. But to actually say whether it's 10 times or 2 times or more, I should probably do a GNN where you don't have edge attributes and do that comparison, which I have not done yet. But yeah.
Next question is very fundamental, very deep.
Yes.
It can be used to actually explain the challenges for any next word prediction, any statistical logistic method purely based on corpus or data, and why they would have challenged. Because there's so much involved. What are you considering about Earth or Pluto? And we use the knowledge that we got about planet. Does that knowledge automatically get incorporated if you try to take any of the neural network based approach? Any, or you have to incorporate that, or you're guided to really incorporate that, which otherwise it will in general would not typical, right? So yes, there is a massive, benefit of massive data, but then there is some sort of steering necessary to bring in the semantics, additional knowledge necessary for any of this question. Relatively simple looking analogies is making so much assumption about additional context and knowledge that how much the models language models can do is an important question, and how you complement them is a very important question. And we can use that to explain further in the next work that will be very useful.
Because recently now people are looking at analogies in the sense far and close, in the sense if the domains are close by, how would you see analogies? And if domains are far away, how would you identify? So I think what you are suggesting is also complementary to that on nodes and relations. So it's an interesting balance to look into.
I had a generic question, I guess, but I just wanted to give me a panoramic view of how neural networks and various neural network models are used in the various pipelines that you have described, that work with. Just
High level. So one is we just prompt, we just talk. So nothing else, we just talk like prompting. So that is one way that we did. And then we actually encoded whatever we had. So we send it through basically the LLM, get the embedding. So we send then it's more numbers and all that, not just talking. So that is one way. What else that we did? Yeah, that's basically two very high levels. I think we did a lot of prompting, or maybe a balance, but anyway, we did a lot of prompting because a lot of these newer models, so they claim they are very good. You don't have to train or anything, right? You just ask something. So we just asked to see how good they are. But in previous cases, in my EACL work and others, we looked a bit at inner workings and probing. So that is, yeah, looking inside.
thank you. So we still have okay. Um, for proportional analogy, one of the examples was oxygen and gas. So there's this purely statistical approach. If you ask which is the most common verb in sentences involving oxygen and gas, you get a result, produce, and then some others that are less common. So you could then take the 5 candidate answers that you have and find out which of those pairs most commonly uses the word produce in a sentence, and choose that.
True.
How would that compare to your approach?
So in my approach,
And that requires no semantics.
yeah, nothing.
No syntax, other than you have to know
Statistics.
what a verb is.
And probably the general statistics of how those two.
The LLM has to know what a sentence is and has to know what a verb in the sentence might be, but that's all. So how would that compare?
So I think
would that be better than chance?
I think that might be better than chance. But if I remember correctly, there are previous work that kind of try to look into this statistical based method, I'd say. Very initially, there was the very first work that from 2008 from Ijkai paper that kind of introduced not the exact way that you are explaining, but similar statistics-based method for that. LRA, I forgot the longer name, but they did fairly well, but not very well. So there were other methods after that that performed better. So in a sense, right, if LLMs, so they do just more than identifying probably these other verbs, because the corpuses that they are trained is massive. So they are capturing a lot more than that. Okay, these verbs come together maybe lots of times, but much more than that. So I think that approach is better than chance, but not very much better than chance.
Could you try that?
Amit, we are very, I mean, we won't have much time for the closed session. So we, both Val and I have hard stops at 12. So
Well, let us finish this line of questioning. We, so you might consider just adding that example.
Yes.
Um, I have one more question, sorry to dominate this. And sort of moving forward, analogies help people understand things. So people can see and imagine planets moving around the sun. Initially, when atoms and electrons were first introduced, they had a hard time conceptualizing it. The analogy helped them understand it. So could analogies help LLMs answer questions? Basically, could you add an analogy to a prompt and help the LLM generate a better response?
I have tried doing this, not necessarily to try to see whether they can create a better answer, but in most of the cases, what they would do is they would also give back an analogy to explain something. And what I've seen, those analogies sometimes, if there's like very easy concepts to match, the analogy would be probably, I've seen very strong ones. But if they're very far apart and not so much close by, I've seen that they're like superficial, and there's like, you can feel that this is not necessarily analogy, but it is trying to make it look like an analogy kind of thing. But I've not done specific research on that line. That is what I've observed though.
Let us now ask the audience if they have any questions before we get into closed session. Let's see if it's someone there. Just a quick question, right? So you talked about how technology can start each concept. How do you see the use of this work beyond teaching concepts? So students also using it for explaining the relations, model for just operations feedback.
So, one thing I was just thinking very recently was there are agents now everywhere. So, there could be agents that are in situations like edge cases. So, how would I behave in this edge case? So, they could make an analogy to a case that they have seen before, right? That type of thing would be a very recent one for this agentic era.
Well, if there are no more questions from the general audience, either online or in the room, we'll move to closed session. So I'm going to ask the last part, okay?